April 7th, 1989, the Norwegian Sea, 180 kilometers southwest of Bear Island, in the gray freezing expanse of open water separating mainland Norway from the Arctic archipelago of Svalbard, a Soviet nuclear submarine was running at patrol depth on a routine combat deployment. At 11:03 in the morning, a catastrophic fire ignited in the rearmost compartment of the vessel. Within minutes, the blaze had consumed the available oxygen, overwhelmed the onboard fire suppression system, and triggered a sequence of cascading engineering failures that the designers who built this submarine had identified as a theoretical risk years before it entered service. The Soviet Navy had reviewed those risk assessments, they had classified them, and they had sent the submarine to sea anyway. 42 men died in the Norwegian Sea that morning. The investigation that explained precisely why they died was locked in a classified filing cabinet for nearly 20 years. The families of the dead received a sanitized account. The engineering findings, the specific, documented, pre-identified vulnerabilities that had compounded the disaster, were buried inside the archives of the Malekith Design Bureau and the Soviet Ministry of Defense, inaccessible to anyone without the highest security clearance. The submarine was the K-278 Komsomolets. It was not a standard vessel. It was a one-of-a-kind experimental prototype that had broken the world depth record 4 years earlier, diving deeper than any military submarine in human history. The precise engineering decisions that made it extraordinary were the same decisions that made it uniquely, specifically, and catastrophically vulnerable to the exact sequence of events that destroyed it on April 7th. To understand what the classified investigation actually found, you have to start with the engineering problem the K-278 was built to solve. By the early 1970s, the Soviet Navy faced an anti-submarine warfare threat that was steadily closing around their strategic nuclear forces. The United States had spent decades constructing an integrated detection network of extraordinary scope and sensitivity. On the ocean floor, the sound surveillance system, hydrophone arrays carpeted the North Atlantic from the Greenland, Iceland, UK gap southward. Above the water, P-3 Orion maritime patrol aircraft patrolled enormous sectors of ocean, seeding the surface with expendable sonobuoys and using magnetic anomaly detectors to locate submerged submarines from altitude. Beneath the surface, a growing fleet of Los Angeles-class hunter-killer submarines, equipped with the advanced BQQ-5 sonar suite, was actively prosecuted Soviet submarines attempting to transit into the open Atlantic. For the planners in Moscow, this represented an existential vulnerability. Soviet ballistic missile submarines could be tracked from the moment they left the shallow coastal waters of the Kola Peninsula. In wartime, they would be hunted and potentially destroyed before reaching viable launch coordinates. The Bastion strategy, keeping submarines in the defended waters of the Barents and White Seas, partially addressed this vulnerability, but it also constrained the operational flexibility of the entire sea-based nuclear deterrent. Soviet naval planners began developing a supplementary strategic concept built around a single physical reality: depth. If a submarine could dive deep enough, it would physically escape the effective performance envelope of American anti-submarine weapons. The Mark 46 lightweight torpedo, the primary anti-submarine weapon carried by American patrol aircraft and surface ships, was optimized for medium-depth engagements. Towed sonar arrays towed by surface vessels lost effectiveness below certain thermal layers. At extreme depth, the specific acoustic propagation characteristics of the deep ocean created shadow zones that could theoretically render a submarine acoustically invisible to surface detection systems. The theoretical threshold depth that Soviet naval engineers identified, below which American detection and attack systems would be severely degraded, was 1,000 meters. The mandate issued to the Malekith Design Bureau in Leningrad was unambiguous: design a nuclear-powered combat submarine capable of sustained operational patrol at 1,000 meters below the sea surface. This was not a gradual evolution from existing designs. It was a fundamental engineering departure. No military submarine had ever been designed to operate at that depth. The physics of that requirement began with one immovable constraint that would define every subsequent decision the Malekith engineers made: the material of the hull. At sea level, atmospheric pressure is approximately 14.7 pounds per square inch. For every 10 meters of water depth, pressure increases by approximately one additional atmosphere, roughly 14.7 additional pounds, pressing inward on every square inch of exposed hull. At 1,000 meters, the external pressure on a submarine hull reaches 100 atmospheres. That is 1,470 pounds of compressive force pushing inward on every single square inch of the pressure vessel's exterior surface, simultaneously, continuously, without pause. Conventional high-tensile steel, the material used in every operational submarine in the Soviet Navy, reaches its structural limits well before 1,000 meters. The wall thickness required to resist 100 atmospheres of compression in a steel cylinder of practical internal diameter would add so much mass to the vessel that it would lose positive buoyancy entirely. Steel, at 1,000 meters, is not a viable pressure hull material. The Malekith engineers had one alternative that the physics of the problem would permit: titanium alloy. Certain titanium alloys possess a strength-to-weight ratio that dramatically exceeds that of high-tensile steel. The titanium grades available to Soviet metallurgists in the mid-1970s, developed specifically for military aerospace and naval applications, could theoretically sustain the compressive loads of 1,000-meter depth while keeping the hull mass within limits that allowed the submarine to maintain positive buoyancy. On paper, the solution was clear. In practice, working with titanium on the scale required to build a nuclear submarine was an industrial challenge of a kind that the Soviet shipbuilding industry had never previously encountered. Titanium is chemically reactive at elevated temperatures. Unlike steel, which can be welded using conventional arc welding processes with appropriate shielding gas, titanium at welding temperatures immediately oxidizes on contact with atmospheric nitrogen and oxygen. This oxidation does not simply discolor the weld. It creates a brittle, crystalline boundary layer within the metal that severely compromises the structural integrity of the weld seam. The titanium weld exposed to air during fusion is a failed weld. It will not hold at depth. It will not survive the compressive loads of the operational environment. To produce watertight, structurally sound titanium welds, every single joint in the K-278's pressure hull had to be performed inside a sealed, inert gas atmosphere. The Sevmash shipyard in Severodvinsk constructed specialized welding enclosures, sealed chambers flooded entirely with argon gas, in which highly trained welders worked in full protective equipment to fuse the hull sections with the atmospheric oxygen entirely removed from the working environment. The process was extraordinarily slow. A weld that would take hours on a steel hull took days on a titanium one. The argon chamber had to be purged and verified before each session. The titanium alloy billets had to be sourced from specialized mills operating under strict metallurgical controls, because any impurity in the base metal would propagate through the weld and compromise the final joint. The entire construction process was a logistical exercise in controlled precision at a scale that strained the capacity of the Soviet military-industrial infrastructure. The Malekith engineers overseeing construction at Sevmash knew that the K-278 was carrying no margin for error in its structural welds. The design pressure depth was 1,000 meters. The calculated crush depth, the depth at which the titanium hull would fail entirely, left a specific engineering safety margin above the operational depth. That margin was not generous. It was precisely calculated. Every weld that fell outside the quality specification narrowed that margin. In a steel submarine at conventional depths, a substandard weld might result in a slow seam leak that damage control teams could manage over hours. In a titanium submarine at 1,000 meters, a substandard weld under 100 atmospheres of compression would fail without warning, without time for response, with total and instantaneous consequence. The K-278 Komsomolets was commissioned in 1984. In 1985, during deep diving trials in the Norwegian Sea, it dove to 1,020 meters, a world record for military submarines that has not been broken by any Navy since. At that depth, the titanium pressure hull compressed measurably. The internal diameter of the crew compartments physically shrank by several millimeters as the external pressure loaded the structure. Systems throughout the submarine had been pre-engineered to accommodate this deformation. Pipe joints, cable runs, valve seats, every component whose performance depended on specific dimensional tolerances had been specified with the depth compression accounted for. The record dive was celebrated within the Soviet naval establishment. The K-278, was proof that the Malakit Bureau and the Sevmash shipyard had solved one of the most demanding engineering problems in the history of submarine design. The Soviet Navy had a submarine that could disappear below the effective reach of American weapons. What was not celebrated publicly, and what the Malakit engineers understood with uncomfortable clarity, was that achieving 1,000-meter operational depth had introduced a life support architecture into the K-278 that created a specific vulnerability the engineering team had analyzed, documented, and never fully resolved. That vulnerability was fire. Every nuclear submarine carries its crew inside a pressure hull that is, fundamentally, a sealed container. The atmosphere inside that container must be actively managed. CO2 produced by the crew's respiration must be removed. Oxygen must be replenished. On conventional submarines, this is accomplished through a combination of stored compressed oxygen bottles and chemical CO2 scrubbers. The K-278's design philosophy introduced a different architecture. The operational requirements, extended patrols at extreme depth, with the crew potentially isolated from emergency resupply for weeks, demanded a life support system that was self-contained and did not rely on large reserves of compressed gas. Large high-pressure oxygen cylinders add mass. They add volume. In a titanium hull optimized to the absolute physical limit of what the material could sustain, every kilogram and every cubic centimeter of internal volume was accounted for. The solution was a regenerative oxygen system built around potassium superoxide, KO2, packed into chemical cartridges distributed throughout the submarine's atmosphere management network. Potassium superoxide reacts with exhaled moisture and CO2 to release fresh oxygen while absorbing the carbon dioxide. The system is compact, reliable under normal operating conditions, and does not require external gas supplies. Soviet submarine designers had used similar chemistry in earlier vessels. It was a proven technology. Potassium superoxide has one physical property that is not negotiable and not variable. It is a powerful oxidizer. When a KO2 cartridge is exposed to direct heat and flame, not the exhaled breath of a breathing crewman, but actual combustion, it does not simply continue releasing oxygen at its normal rate. The thermal energy drives an accelerated decomposition reaction. The cartridge releases oxygen at a dramatically higher rate than under normal operating conditions. In the presence of a fire, the very cartridges designed to sustain the crew's lives actively feed the flames. The Malakit engineers had modeled this risk during the design phase of the K-278. Their fire risk assessment was formal and documented. It acknowledged that the regenerative life support system created an elevated oxygen concentration environment within the submarine's compartments under normal operating conditions, measurably higher than standard atmospheric composition. The significance of this is not abstract. A higher ambient oxygen concentration does not merely support combustion more readily. It lowers the ignition threshold of materials that would not catch fire under standard atmospheric conditions. Hydraulic fluid vapor, cable insulation compounds, the lubricant residue present on every mechanical component in a working submarine. All of these have flashpoints. All of those flashpoints decrease as ambient oxygen concentration increases. The engineer's conclusion was that the risk was acceptable given the compartmentalization of the vessel. The K-278 was divided into 7 watertight sections, separated by pressure-resistant bulkheads. The LOKH fire suppression system, a halon-based network designed to flood an isolated compartment with inert gas, starving a fire of its oxidizer, was installed throughout the submarine. Their fire propagation models showed that if a fire ignited in any single compartment, a competent crew could seal the relevant bulkheads within a specific response time window and activate the LOKH system, containing the blaze before it reached adjacent compartments. Those models were not wrong. The physics they described was accurate. What the models could not fully account for was the specific, chaotic, smoke-filled reality of managing a rapidly accelerating fire inside a sealed metal tube, in the dark, at depth, with crewmen simultaneously fighting the fire and attempting to execute emergency procedures under extreme psychological stress. On April 7, 1989, the K-278 Komsomolets found the gap between the model and the reality. The fire ignited in compartment 7 at 11:03 a.m. Compartment 7 was the rearmost section of the submarine, housing the aft electrical distribution systems and mechanical equipment associated with the propulsion train. The precise source of ignition has never been officially confirmed. Evidence examined in the investigation pointed toward a high-pressure hydraulic line failure that sprayed flammable fluid across electrical contacts, a scenario that had occurred in Soviet submarines before and had been manageable in standard atmospheric conditions. In the elevated oxygen atmosphere of Compartment 7, it was not manageable. The initial combustion was immediate and violent. The duty officer initiated the LOKH fire suppression system within minutes of the ignition. The halon gas discharged into Compartment 7. The investigation would later determine that the specific geometry of the fire, its location relative to the compartment's ventilation structure and the volume of burning material already involved, meant the halon concentration never reached the extinguishing threshold. The gas displaced some oxygen from the compartment. The fire continued. The heat from the burning aft compartment rapidly began affecting systems beyond the fire zone. The main electrical bus bars serving the aft propulsion systems were inside or immediately adjacent to the burning compartment. Within 20 minutes of ignition, the K-278 began experiencing progressive loss of propulsion control. The commanding officer, Captain First Rank Yevgeny Vanin, ordered an emergency ascent to the surface. As the submarine began rising, a secondary physics problem compounded the emergency. The reduction in external pressure as the K-278 ascended caused the atmosphere inside Compartment 7 to behave differently. The partially automated ventilation system, designed to maintain pressure equalization across the submarine's internal spaces, began drawing atmospheric flow toward the fire as pressure differentials across the bulkhead connections changed. The burning compartment was being ventilated, not by deliberate human action, but by the automated mechanics of the pressure management system operating as it was designed to operate under ascent conditions. The steel bulkhead separating Compartment 7 from Compartment 6 began to heat. The insulation on electrical cable runs passing through pressure-resistant penetrations in the bulkhead, a necessary architectural feature of any compartmentalized submarine, began to smolder. The fire now had a thermal pathway into the adjacent compartment. At 11:52 a.m., less than an hour after ignition, the K-278 broke the surface of the Norwegian Sea. The distress signal was transmitted immediately. The Northern Fleet Command at the Kola Peninsula received the call. Aircraft were scrambled. Surface vessels were ordered to the position at maximum speed. The nearest Soviet rescue assets were more than 3 hours away. On the surface, the situation appeared to offer options that it did not actually possess. The reactor had scrammed correctly. The automatic insertion of the control rods had halted the nuclear fission chain reaction, removing the most catastrophic possible outcome from the emergency. The submarine was afloat. Some crew members were fighting the fire with portable extinguishers. Officers assessed the situation and made the decision to open hatches in the aft section to ventilate the burning compartments and allow firefighting teams better access. What that decision introduced into a compartment burning in an oxygen-enriched atmosphere was a direct supply of fresh atmospheric air. The fire that had been consuming available oxidizer inside a sealed compartment, potentially trending toward oxygen depletion and self-extinction over time, received a massive influx of additional oxygen through the open hatches. Witnesses on the bridge described a sudden, dramatic intensification of the fire in the moments after the hatches were opened. The engineering team at Malekith had documented this specific scenario in their fire risk models. Under high oxygen concentration conditions, ventilating a compartment fire is not firefighting, it is acceleration. For 5 hours, the crew fought the fire on the surface of the Norwegian Sea. The K-278's structural integrity held. The titanium hull, subjected to internal heat loads it had never been designed to sustain, deformed but did not rupture through the main pressure hull sections. The propulsion systems remained inoperable. The submarine drifted. At 17:08 p.m., 6 hours after the initial ignition at 11:03, the K-278 Komsomolets sank. The fire had burned through critical hull penetrations in the aft section, compromising the watertight integrity of the pressure vessel at specific structural boundaries. The flooding was not gradual. The submarine went from flooded to fully submerged within minutes. Of the 69 men aboard, 27 reached the surface and survived in the freezing Norwegian Sea until rescue arrived. 42 did not. Of those 42 deaths, not all occurred during the fire or the immediate sinking. The most operationally significant, and from an engineering standpoint, the most damning, deaths occurred after the submarine was already on the bottom. The K-278 Komsomolets had been designed with an emergency survival system that was, in concept, a genuine engineering innovation. It was designated the VSK, the Vysplyvajushchaya Spasatelnaya Kamera, the floating rescue capsule, and it was embedded within the structure of the submarine's sail. The rationale behind the VSK was a direct consequence of the depth requirement. At 1,000 meters, a standard submarine escape trunk, a pressurized airlock from which a crewman can swim out individually and free ascend to the surface, is physically lethal to use. The pressure differential between the flooded submarine and the surrounding ocean at that depth is so extreme that no human body can withstand the decompression of free ascent from 1,000 meters. Standard escape training is irrelevant below a few hundred meters. The VSK addressed this problem by eliminating the individual escape requirement entirely. In an emergency, the entire crew of the K-278 could seal themselves inside the rescue capsule. The pod would then separate from the submarine hull and ascend independently under its own buoyancy, carrying the crew from any depth to the surface inside a pressurized container. The crew would experience no pressure change whatsoever during the ascent. They would emerge on the surface inside a sealed, survivable environment and wait for rescue. The system had been tested. The VSK had been validated through qualification trials at controlled conditions. The hatch mechanism had been inspected, certified, and cleared for operational use. On paper, the VSK was the safety system that made operating a 1,000-meter submarine survivable in an emergency. As the K-278 began its final descent on April 7th, a group of surviving crew members made their way to the sail and entered the VSK capsule. They sealed the hatch and initiated the separation sequence. The capsule released from the sinking submarine. It ascended. It reached the surface. The hatch failed to open. The primary escape hatch of the VSK, the mechanism through which the survivors inside the capsule would exit onto the surface of the Norwegian Sea, had deformed. 6 hours of internal fire damage. 6 hours of thermal loading on the steel structure surrounding the capsule. The rapid pressure changes of the submarine's emergency ascent and subsequent uncontrolled descent. The mechanical stresses transmitted through the whole structure as the submarine struck the bottom. The combination of these loads, which had never occurred simultaneously in any test the Soviet Navy had ever conducted, had microscopically deformed the hatch sealing surface against its frame. When the men inside the VSK attempted to open the hatch, seawater under the residual pressure differential of the partially flooded capsule forced its way through the imperfect seal. The capsule that had successfully ascended to the surface, that had functioned as designed in every measurable engineering parameter of its deployment sequence, drowned the men who had made it to the top. The Malekith engineering team had identified thermal deformation of the VSK hatch as a potential failure mode during the design review process. Their assessment had concluded that the probability of the specific combination of fire damage, structural loading, and rapid depth cycling occurring simultaneously was sufficiently low to fall within acceptable risk parameters. The families of the men who drowned inside the capsule, while it sat on the surface of the Norwegian Sea, would eventually learn that their deaths had been assessed as an acceptable risk before the submarine ever left the shipyard. The Soviet Navy's formal public response to the loss of the K-278 followed the institutional procedures that had governed Soviet military disaster communication for decades. The official announcement acknowledged the loss of the submarine and confirmed crew fatalities. Captain First Rank Vanin, who went down with the ship, was awarded the title Hero of the Soviet Union posthumously. Surviving crew members received decorations. A state funeral was organized with appropriate honors. The public statement described a fire that had been fought with courage by a skilled crew and that had resulted in the tragic loss of the vessel. What the announcement did not describe was the engineering findings of the investigation that immediately followed. The Soviet Ministry of Defense and the Naval General Staff established a commission to review the loss of the K-278. That commission had access to every document the Malekith Design Bureau had produced in connection with the K-278's design, construction, and qualification. The commission reviewed the pre-operational fire risk assessments. It reviewed the LOKH system's performance specifications against the documented timeline of events on April 7th. It reviewed the VSK qualification test records against the failure mode that had killed the men inside the capsule on the surface. The Commission's findings were classified at the highest level of Soviet state secrecy. The families of the 42 dead received no technical information about the factors that had contributed to the loss of the submarine and the loss of life. Naval officers who had reviewed the investigation files were bound by their security oaths. The engineering vulnerabilities documented in the design phase, the fire propagation risk created by the potassium superoxide life support system, the specific gap between the VSK test conditions and the conditions of an actual emergency. None of it reached the people who had lost fathers, sons, and brothers to those vulnerabilities. For the remainder of the Soviet era, the classified status of the K-278's technical specifications provided an institutional barrier against any public engineering discussion of the disaster. The submarine was classified. The investigation was classified. The specific questions that would have forced the responsible engineering institutions to account for what they had known before the fire. Those questions could not be asked publicly because the documents that would have framed them were locked in archives that did not officially exist. The K-278 Komsomolets lay on the seabed of the Norwegian Sea at 1,685 meters, deeper than any recovery technology available to either the Soviet Union or its successor state could reach. The 2 nuclear torpedoes remaining in the forward compartments and the enriched uranium fuel slowly corroding inside the reactor core meant that the wreck was not merely a memorial. Norwegian and Russian environmental monitoring teams conducted periodic water sampling above the site throughout the 1990s. They found elevated concentrations of cesium-137 in the water column immediately above the wreck, consistent with slow seepage through corroding hull sections. The wreck was leaking. The Russian Navy, operating in the financial catastrophes of the post-Soviet decade, could not fund a serious recovery or remediation operation. The monitoring continued. The cesium continued to seep. The families of the dead continued to press the government for the full investigation findings. They were refused repeatedly on grounds of state security. The partial disclosure that finally emerged came not through any official act of transparency, but through the work of Russian journalists and independent naval historians who operated in the increasingly open public environment of the late 1990s. Former engineers and naval officers, speaking anonymously, began describing to investigative reporters what the internal investigation had actually documented. A former member of the Design Bureau's Fire Safety Analysis team described the pre-operational risk assessment of the KO-2 system in terms that confirmed precisely what the families had suspected for years. The fire scenario of April 7th was not an unforeseeable accident. It was a scenario the designers had modeled. Civil litigation brought by survivors' families against the Russian Ministry of Defense forced partial disclosure of specific technical documents through the Russian court system. The deposition testimony of naval engineers, compelled under civil discovery, provided fragments of the investigation's findings. A partial transcript of the Commission's technical conclusions reached investigative journalists in the early 2000s through sources who have never been publicly identified. The picture those fragments assembled was specific. The LOKH fire suppression system had not failed mechanically. It had operated within its specified performance parameters. What the system could not overcome was the oxygen-enriched atmosphere of the burning compartment. The elevated oxidizer concentration generated by the KO-2 life support cartridges, accelerating the fire's heat release rate beyond the threshold at which the halon concentration could achieve extinguishment. The LOKH system had been specified for a standard atmospheric fire. April 7th was not a standard atmospheric fire. The VSK hatch failure analysis in the classified commission report was, according to sources who reviewed it, unambiguous in its identification of the failure mode. Thermal deformation of the hatch sealing surface under combined fire damage and rapid pressure cycling. This failure mode had been categorically identified during design review. It had been assessed as low probability. The Commission found that no design modification to address the identified failure mode had been implemented before the submarine entered service. The full, unredacted investigation report has never been officially released. The Russian government has maintained that the relevant documents remain classified for national security reasons. The families of the dead have never received an official technical accounting that matches what has since emerged through non-official channels. Naval engineers and historians who have studied the K-278 Komsomolets in the decades since the disaster have consistently reached a conclusion that is precise and uncomfortable. The submarine did not sink because of a single catastrophic mistake. It did not sink because a weld failed or a valve was improperly installed or a crew member made an obvious error. The K-278 sank because of the accumulated gap between the performance of its safety systems under the conditions in which they were tested and the conditions in which they were actually used. The LOKH fire suppression system was correctly designed for the fire scenarios the engineers modeled. It was not designed for a fire in an oxygen-enriched atmosphere because the engineers' modeling assumed the atmospheric chemistry that existed in their test environment. The VSK hatch mechanism was correctly designed for the pressure and thermal conditions of the qualification trials. It was not qualified to the combined load state that existed after 6 hours of fire damage, structural deformation, and a rapid, uncontrolled descent. Every system that failed on April 7th had been inspected. Every system had been certified. Every system had met its specified performance requirements. The systems failed because the specifications were written for conditions that did not precisely correspond to the ones in which they were used. This is not an obscure or exotic engineering lesson. It is one of the most consistently repeated findings in the forensic analysis of major engineering disasters across industries and across decades. The failure modes that kill people are almost always the failure modes that fall at the intersection of multiple concurrent conditions, combinations that exist just outside the boundary of any single test regime or safety analysis model. The Soviet Navy classified those findings for nearly 20 years because acknowledging them publicly would have required acknowledging that the institutional process used to design, qualify, and clear the K-278 for operational service had failed to adequately address known, documented risks. That is not an accusation that any military institution finds comfortable to make about itself in public. Secrecy was not only operationally convenient. For the institutions involved, it was institutionally necessary. The K-278 Komsomolets remains on the floor of the Norwegian Sea. No crew has been recovered. Russian environmental monitoring of the site continues, though the frequency and public disclosure of results have varied across different government administrations. The reactor core continues its slow radiological decay at 1,685 meters in the dark. The depth record the submarine set in 1985 has not been broken. The titanium hull that allowed it to dive to 1,020 meters. The extraordinary product of the specialized argon atmosphere welding chambers at Sevmish and the metallurgical engineering of Soviet titanium mills proved structurally sound throughout the disaster. The hull that the engineers built did exactly what the engineers designed it to do. The hull was not the failure. The engineering legacy of the K-278 is not a story of technical incompetence. The Malekith Design Bureau built a machine of genuine and unprecedented capability. The submarine achieved its design depth. Its structural engineering was validated under the most demanding conditions possible. The men who designed the titanium hull and its compartmentalization architecture produced work that held together through 6 hours of internal fire and a subsequent sinking. That is not a trivial engineering achievement. What the K-278 stands for in the history of naval engineering, and what the classified investigation documented in findings the Soviet Navy buried for 2 decades, is the gap between engineering validation and engineering reality. The gap between a system that passes its qualification tests and a system that performs under the specific, unrepeatable, chaotic conditions of an actual emergency. The gap between a risk that has been assessed and documented and a risk that has been actually mitigated. 42 men died in that gap. For nearly 20 years, the men and women who loved them were told a story that left that gap unnamed. The engineering story behind their deaths, the specific, documented, pre-identified vulnerabilities that intersected catastrophically on April 7th, 1989, deserve to be examined fully in public by the institutions responsible for it. It was not. The files were locked. The answers came in fragments through journalists and lawsuits and anonymous testimony delivered decades too late to matter to the people who needed them most. The K-278 Komsomolets is remembered today as the deepest diving military submarine ever built. That is true, and it is remarkable. It is also the least important thing about it.